to the rest of the story. Although I did want to go back to a couple exercises based on, so first a couple more exercises. Based on that material, and then I'll go on to new material. So first, I wanted to just say that the map from gamma 1 R2, that's the Mobius bundle, and that's the space of lines in R2 along with a point on the line. If I just take that point, that's a map to R2. This is called the blowup. Of R2 at 0. So this is a model for something which is useful. And one exercise is show, if I let W be this represents, so show tau W is a generator for H upper 0. Of course, that's the only cohomology group. This is just, the main technical point is, oh wait, if you look at it, the pullback is gonna generally be a point, but there's maybe some bad points around the origin, but it's really a matter of showing that this is a valid Thom class, and just so mainly convince yourself yourself in the process, which is maybe harder. That the the injectivity, the fact that if I call this P inverse 0 is RP1 is not an issue. But yeah, this is a fun, just a fun map. I mean, you're really thinking, you've got the Mobius bundle and you're making R2, those should all go through the same point there. You're sort of filling in R2 through these lines, and you're hitting 0 extra once for every line, and yeah, so it's a and this was part of our basic definition of characteristic classes. What else? What we right more generally. If we put a metric on this bundle, say by putting a metric on Rn, and we take the disk bundle, gamma 1 Rn, and say quotient by the sphere bundle, first of all, show that that's homotopy equivalent to Rpn, and moreover, if I take this map where again these are lines in Rn and a point on the line, and I send it to the point in Rn, and if I've made my metric on this bundle by just choosing the standard metric, say on Rn, and using that to say what the unit vectors are, what the scale is on this bundle, then this will actually go to Dn. And so what we can do is quotient by Sn. Sn minus 1. And the claim is that this is the kind of standard map, which is the quotient by the n minus 1 skeleton. Let's see, anything else I want to do? So, an elaboration here, some more generally. Say for compact manifolds, or you can generalize this. So let me just say related. If W is to M as a degree 1, 1 mod 2 if you're not oriented, or on a degree 1 if you are oriented, map between closed manifolds, a compact manifolds without boundary, then tau W is a generator of H0. So we've got that related fact. And then related to the last lecture, we have a detail kind of related to this very first exercise, this way of the fact that the blow up of R2 doesn't change the fact the identity from R2 itself is also a great representative for the generator in cohomology. Show that the subspace, so remember we had this subspace of pairs of lines in the bundle E direct sum F of line bundles. Inside there, I had L1 and L2, so that the first one is equal to F. Show that this represents, so this then sits over E plus F, because E plus F plus E plus F. And so, but that's homotypically equivalent to whatever our base manifold is M. So show that this represents W1E. It's not quite the same as the inclusion of a fiber. There's, I think, a blow up involved, and that's why I gave the first exercise. And then also, I hesitate to call this an exercise, but you can sort of fill in details if you can to establish Whitney sum for, say, E rank 2, F rank 1, by considering through defining a W. I'm going to sketch. So here, again, E is rank 2, F is rank 1, and what we're going to look at are pairs of lines L1 and L2, so that and a point on each, and a point on each in such that I mean, so I'm not 100% sure, but basically, generically at least, they project, which project to the same line in E, and what I'm not so sure about is if L1 equals F, but L1 is sort of closer to F, while L2 is closer to E. And I claim that this will also have sort of three boundary pieces, one where L1 equals L2, and that's going to be the second Stiefel-Whitney class, L1 equals 0, and L2 equals 0. So this is, again, to establish that W2 E plus F is W2E plus W1E W1F. I think this is the right submanifold, or submanifold with corners to look at. And notice that closer, by the way, is always going to happen. Like one of those is going to be closer. If they project to the same place in E, then one will be sort of on top of, will have a greater F coordinate for the same projection down below. That's what we would mean by closer to F. Okay, so those are a few exercises. Now let's get to the lecture. So yeah, we've got a very, hopefully, this will be fairly short and sweet. I want to talk about the main sort of universal pullback representing object result. That's a key central part of the theory of characteristic classes. Let me just first say R infinity is going to be the colimit of Rn. So that means that it's a space which any point is really in the image of some finite Rn. So the coordinates are eventually all 0. So this is a version of infinite dimensional that's one of the weakest, so to speak, but it's the one that's comes up probably the most in topology. And I'm going to modify a definition because I realized I was inconsistent with some other notation before. So a bundle is tame if it is a subbundle of X cross R infinity considered as a trivial vector bundle. All our bundles that we study are finite rank. We're not going to get into the infinite rank case in any serious way, but we'll introduce this one quote unquote infinite rank bundle just to say you're tame if you sit in there as a sub bundle. So the previous tame, so if you're let me modify the previous notation. A bundle is finite type. That's the language used in Milnor and Stasheff. If it's a subbundle of X cross R in for some n. So finite type are tame, but tame is a bit more broad. And and then you've got results so that so all bundles over compact or even paracompact, which is most spaces you'd want to study, base spaces are tame. It's again, that's a partition of unity argument. I think I gave it, but you can also compare with a finite base case, but then the paracompact is a straightforward. So compact is treated in lemma 5.3 in Milner and Stasheff. And so so let's just say that vect in X is the set of isomorphism classes of, let's just say the tame ones, but that's all if you're tame rank n vector bundles. Over X. And then the theorem, that's all I want to talk about today, is the fact that vect in X is isomorphic as sets to this, the set of homotopy classes of maps from X to the Grassmannian of n-dimensional subspaces of R infinity. So that's, this is called a representability theorem. So the way to say this is that GRN R infinity represents the functor vect in. And this is something that's useful. That's one of the you know, in this book, categories for working mathematicians. You've got things like the innate lemma, etc. Thinking about when a functor is representable in a category. Representable means it's expressible as homomorphisms in the category into some object or from some object. So, I mean, in some cases, homotopy groups are, you know, that's often said co-representable because it's maps from spheres. You know, another example, sort of a, and this is actually a bit of a cousin, we'll talk about that later, is that actual representations, which you start saying it's okay, group actions on vector spaces, that's represented by maps from the group into GLN, you know, over the field that we're doing our representations. So, so this is akin to that, or more generally, yeah, G representations in any category are the same as maps from G to the automorphisms of an object in that category. Okay, so this is what we want to prove. I mean, so this quote unquote reduces the study of vector bundles to some homotopy theory, and then, you know, something to say is this is difficult to calculate. In general, let me just say in general, maps between any two spaces, if I pick them out of a hat, or even some fairly nice ones like BUN, is difficult to calculate. The most famous example being spheres, but are all maps from 1,000 sphere to a, or 2,000 sphere to a 150 dimensional sphere. We have no idea. Nobody on the planet has, I mean, I guess there's some results, but yeah. So if I just take two spaces out of a hat, especially if they're finite complexes, or even most co-limits of finite complexes, this is going to be difficult to calculate. So this is a really wonderful conceptual result. We'll talk about its consequences at the end for characteristic classes, but it's not like, oh, we reduced it to homotopy theory, and homotopy theory is easy, so now I can tell you what vector bundles are. Nope. In fact, one of my students, PhD students, is trying to make new calculations of this using various, very modern approaches to both homotopy theory and, in particular, the vector, the Grassmannians. There's something called the orthogonal calculus, which gives new approaches to Grassmannians. Okay, so let's have the proof. So we're just gonna talk about how you go back and forth between them. So if I have a vector bundle, and it's tame, so that's sitting inside, it can be expressed inside B across R infinity. Let me say that here I have to choose an embedding. That'll be the main point of any work in this theorem. Then what I can do to that data is associate a map to the Grassmannian, which sends, and what I'll do is I'll call it CLE, and it's going to send a point B in B to the V inside R infinity, which sits over, call this map P, but with this inclusion. So in P inverse B is R infinity, but I have this copy of V in there. So at P over B, that's what the data I have, and so that's going to be an element of the Grassmannian. So that's a map from the collection, or a putative map. I made a choice in there. Going the other way, if I have, is even easier. If I have some map from B to GR in R infinity, I'm going to pull back the universal bundle. And the idea is that if these are well defined, then they're clearly inverses. And let's just at least talk through that. Well, what does that mean? That would mean that if I'm going to take, if I've got my E embedded, I take CLE and I pull back the universal bundle, then of course I'm going to get E back again. And on the other hand, if I classify the map pulled back, the map for the vector bundle pulled back from the universal bundle, then I'm going to get F, you know, if we choose the canonical embedding of the pullback. I mean, gamma n is not just a vector bundle, but it's a vector bundle with a standard, a canonical embedding in a trivial bundle. If I choose that as my embedding, then when I classify that, I'll obviously get F. So it comes down to just showing that this is actually well defined. I've got a choice in the first map. In the second one, notice that I'm using homotopy classes of maps, but I'm picking a representative, F. You know, really what I should say here is that I've picked a representative of homotopy class, but then I pull back using using the representative of the homotopy class. And so that second is well defined. As we showed that that bundles B sub t over on, let's see, bundles B sub t, which are restricted from a bundle over B cross I, are all isomorphic. So if I choose a different representative for the homotopy class, of course I have a homotopy between them, I may assume, between F and G. I pull back through the homotopy and then I restrict to both ends, and we show that those are the same. So it's really then showing the first map is well defined, and that just means that I have this choice of embedding. And right. So what we can do is there's a wonderful little Hilbert's Hotel, so to speak, proof of. So we want to say that any two embeddings. So in fact, so why is this? The homotopy class of CLE is well defined since any two embeddings of E in B cross R infinity are homotopic. In other words, there's a one-dimensional family of maps, which of vector bundles from the vector bundle E to this trivial vector bundle, which restricts on both ends to the two maps in question. And this is like a Hilbert Hotel kind of argument. So what you want to do, so you want, so there's a, so you try in general to make a straight line homotopy. If I call these embeddings, I don't know, E1, E2, then I would take T E1 plus 1 minus T E2. I can do that in B cross R infinity. I'm using those T and scalar multiplication and addition in the fibers, right? And that's compatible because I'm in the category of, I'm looking at linear maps on each fiber. But the problem is that every once in a while, maybe these have opposite sign or something like that. And so what you do first you can, you can compose E1 with a map from R infinity to itself, which takes xi to x2i, and E2 with the map which takes the xi coordinate to, say, 2i minus 1. And now they're supported on different coordinates. Each of those, by the way, is I could, if I want, I could make an isotopy because I can sort of do rotation. Just think of the rotation of the x-axis onto the y-axis. So this is isotopic to the identity. By rotations. Oh, that gets me 1. Let's see. Isotopic to the identity by, sorry. Rotation adds a single 0 at the beginning if I rotate the first coordinate to the second and the second to the third. To double the coordinates. Yeah, I think you can just take a straight line homotopy between the identity and the matrix, which represents this this map. So so in any case, my E1 and E2 are each isotopic to this is E1 prime, and this is E2 prime, and these are isotopic through this kind of straight line homotopy. And so that does it. All right, I think that's, so that's the main result for today. And then I wanted to say, so the corollary is that, remember we have these, so let's remember we've got our, by the naturality axiom, for Stiefel-Whitney classes, we can observe and say that any WIE is CL sub E upper star WI of gamma n, the universal bundle here. And so studying the characteristic classes of this one bundle means that somehow we're studying characteristic classes of all of them. So, so the next questions we're going to look at this will be with mod 2 coefficients, and then okay, why are the universal the Stiefel-Whitney classes over those? What are they, and why do they give us the theory that we've come to expect now? All right.